Welcome, dear friend, to a quiet journey beneath your feet. Tonight, as you settle into comfort, we're going to explore the hidden world of earthquakes, not with fear, but with wonder. The ground you stand on is alive in ways you've never imagined, moving and breathing on timescales both impossibly slow and shockingly fast. Before we drift into this geological dream, if you find peace in these facts, a gentle like or subscribe helps others discover this calm corner of the universe. Now, close your eyes if you wish. Let your breathing slow, and let's begin our descent into the sleeping giant beneath us all. The ground moves beneath you right now, not in some distant future, not in faraway lands, but here, at this very moment. Earth's surface shifts about as fast as your fingernails grow, roughly 2 inches each year. It seems impossibly slow until you realize that over your lifetime, the continents will have traveled several feet. Over 1 million years, they cross oceans. This patient migration happens because Earth's solid surface floats on something that flows like honey warmed by the sun. Except this honey is rock-heated to temperatures that would vaporize steel in an instant. Beneath the thin skin we call home lies a furnace of unimaginable power. Earth's core burns at 10,800 degrees Fahrenheit, as hot as the surface of the sun. This internal inferno, fueled by radioactive decay and primordial heat from our planet's violent birth, drives everything. It's the engine that's been running for 4.5 billion years without stopping, the heartbeat that makes earthquakes possible. And yet, we live our entire lives on a crust so thin that if Earth were an apple, our world would be thinner than the skin. But here's what scientists still can't fully explain. Why does Earth have plate tectonics at all? Venus, our sister planet, nearly identical in size and composition, has no moving plates. Its surface is locked solid, a planetary prison of stillness. Mars, once geologically active, fell silent billions of years ago. Only Earth dances this slow continental waltz. Only our world fractures and reforms, destroys and creates. We are the only known tectonic planet in the universe, and scientists still debate exactly why we were granted this geological gift that makes earthquakes and life possible. The Pacific Ring of Fire encircles an ocean like a collar of chaos. This 25,000-mile horseshoe of seismic fury contains 75% of Earth's active volcanoes and experiences 90% of the world's earthquakes. If you traced this ring on a map, you'd draw a line from New Zealand up through Japan, across to Alaska, and down the western coasts of North and South America. Entire nations exist within this zone of constant geological conversation, where tectonic plates meet and grind in an ancient argument that predates humanity by hundreds of millions of years. Every day, Earth experiences about 50 earthquakes, large enough for people to feel without instruments. Most pass unnoticed, gentle reminders in remote regions where only seismographs bear witness. But zoom out further, and the numbers become almost unbelievable. Roughly 20,000 earthquakes occur somewhere on Earth each year that are strong enough to be detected by our global network of sensors. The planet is never still. It trembles constantly, like a sleeping giant, breathing in slow, deep rhythms that occasionally catch in its throat. The largest earthquake ever recorded struck Chile on May 22, 1960. The Valdivia earthquake registered magnitude 9.5, so powerful that it literally changed Earth's rotation. The quake shortened the length of a day by 1.26 microseconds and shifted Earth's axis by nearly 3 inches. This single event released energy equivalent to 178 billion tons of TNT, roughly 25% more than the largest nuclear weapon ever detonated. The tsunamis it generated crossed the Pacific Ocean at 500 miles per hour, killing people in Hawaii, Japan, and the Philippines. A stone thrown into a planetary pond, ripples spreading for thousands of miles. But magnitude measures only energy release, not destruction. The deadliest earthquake in recorded history killed 830,000 people in Shanxi, China, in 1556. Most victims lived in Yaodong's caves, carved into soft rock cliffs that collapsed like avalanches of stone. Entire cities vanished. The death toll exceeded the entire population of many modern countries. All claimed in minutes by a quake we now estimate reached magnitude 8.0. These people had no warning systems, no building codes, no understanding that they'd built their homes along one of Earth's most dangerous fault lines. Japan experiences over 1,500 earthquakes each year that people can feel. That's more than for every single day. Yet Japanese society functions with remarkable calm, having built one of the world's most earthquake-resistant civilizations. Buildings sway rather than crack. Early warning systems provide precious seconds before shaking begins. Children practice earthquake drills the way others practice fire safety. The Japanese have transformed living on tectonic chaos into an art form, proof that knowledge and preparation can soften even the harshest geological realities. Deep beneath the ocean floor, where sunlight has never reached, the longest mountain range on Earth splits the seafloor like a scar. The mid-ocean ridge system stretches 40,000 miles long enough to wrap around Earth's equator 1.5 times. Here, tectonic plates pull apart and molten rock rises from below to create new ocean floor. This underwater mountain chain experiences constant earthquakes, most too deep and distant for human notice. It's a conveyor belt of creation, birthing roughly 2.5 square miles of new seafloor every year. The place where Earth literally grows new skin. Earthquake waves travel through our planet like sound waves through water, but at speeds that would carry you from New York to Los Angeles in under 3 minutes. The fastest seismic waves, called P waves, race through Earth's interior at roughly 15,000 miles per hour. They compress and expand rock as they pass, like invisible hands squeezing and releasing stone. These are the waves that animals might sense before humans, the first whisper of the seismic storm approaching. Behind them come east waves, slower but more destructive, shaking the ground side to side and up and down. These secondary waves travel at about 9,000 miles per hour and cannot pass through liquids of fact that revealed one of Earth's greatest secrets. In 1906, scientists noticed that S-waves from earthquakes would disappear when passing through Earth's core, creating shadow zones on the opposite side of the planet. This observation proved that Earth's outer core must be liquid, an ocean of molten iron and nickel 1,800 miles thick, churning and generating the magnetic field that shields all life from deadly solar radiation. The San Andreas Fault in California slips approximately 1.3 inches per year. That's the same rate the Atlantic Ocean is widening. Over 20 million years, this patient grinding has carried Los Angeles 300 miles northwest from where it began, relative to San Francisco. In another 15 million years, if the current motion continues, Los Angeles will be a suburb of San Francisco. The two cities draw closer by about 2 inches annually, future neighbors sliding toward an eventual collision in deep geological time. But faults don't slip smoothly. Instead, friction locks the plates together for decades or centuries, while stress builds invisibly underground. When the stored energy finally exceeds the strength of the rocks holding the fault in place, everything releases at once. Sections of the fault can leap 20 or 30 feet in a single instant during major earthquakes, releasing strain that took centuries to accumulate. It's like stretching a rubber band slowly, 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 then watching it snap in a blur too fast for eyes to follow. The 1906 San Francisco earthquake ruptured 296 miles of the San Andreas Fault in less than a minute. Fences that crossed the fault were suddenly offset by up to 20 feet, cut and shifted like a photograph, torn and misaligned. Roads that had been straight became broken zigzags. The quake could be felt from Oregon to Los Angeles, from the Nevada desert to ships 50 miles offshore. But the earthquake itself killed only about 700 people. The fires that followed, burning for 3 days through a city built largely of wood, claimed perhaps 3,000 more lives and destroyed 80% of San Francisco. Animals seemed to know. For thousands of years, humans have reported unusual animal behavior before earthquakes. Dogs howling, birds fleeing, elephants running for high ground, snakes emerging from hibernation in winter. In 1975, Chinese officials evacuated the city of Hiking, based partly on reports of animals acting strangely. Hours later, a magnitude 7.3 earthquake struck the city, and the evacuation saved countless lives. Scientists remain skeptical, but curious. Perhaps animals sense the P waves that arrive seconds before destructive shaking. Perhaps they detect changes in groundwater chemistry or electromagnetic fields. We honestly don't know, and the mystery endures. Foreshocks sometimes announce the main event, but often they don't. About 5 to 10% of earthquakes are followed within days by a larger quake, reclassifying the initial tremor as a foreshock in hindsight. But most earthquakes strike without warning, and no reliable method exists to distinguish a foreshock from a standalone event until after the fact. This cruel uncertainty means that every moderate earthquake might be a warning or might be the entire story. The ground keeps its secrets until the moment of revelation. Aftershocks can continue for years. After a major earthquake releases the main strain, the surrounding region adjusts to the new stress distribution through thousands of smaller quakes. The 2011 Tohoku earthquake in Japan, which registered magnitude 9.1, produced aftershocks that continue to this day. Some exceeded magnitude 7.0, powerful enough to cause significant damage on their own. The region trembles as it slowly finds new equilibrium, a process that may take a decade or more, the Earth settling into sleep after a nightmare. The deepest earthquakes occur 400 miles beneath the surface, in conditions that shouldn't allow brittle fracture. At these depths, pressure reaches 1.3 million times atmospheric pressure, and temperatures exceed 2,000 degrees Fahrenheit. Rock should flow like putty, not break like glass. Yet these deep focus earthquakes still happen, caused when cold, dense oceanic plates sink into Earth's mantle and temporarily retain their brittle strength, even in the infernal depths. They're geological ghosts, echoes of the surface world, persisting in an environment that should have erased them. Indonesia holds the unenviable record for most seismic risk. The archipelago nation sits at the junction of four tectonic plates: the Eurasian, Pacific, Indo-Australian, and Philippine plates, all meet and grind beneath these islands. The 2004 Indian Ocean earthquake and tsunami, which originated off the coast of Sumatra, killed approximately 230,000 people across 14 countries, making it one of the deadliest natural disasters in recorded history. The earthquake was so powerful that it caused the entire planet to vibrate by as much as half an inch, like ringing a bell the size of Earth. That 2004 quake lasted between 8 and 10 minutes, the longest duration of faulting ever observed. Most earthquakes finish their terrible work in seconds. Even major quakes rarely rupture for more than a minute. But the Sumatra earthquake just kept going, unzipping 900 miles of seafloor along the boundary where the Indo-Australian plate slides beneath the Eurasian plate. Sections of seafloor jumped upward by 15 feet, displacing trillions of gallons of water and launching the deadliest tsunami in recorded history across the Indian Ocean. The tsunami traveled at speeds up to 500 miles per hour in the open ocean, as fast as a commercial jetliner. In deep water, the wave was less than 3 feet high, passing beneath ships unnoticed. But as it approached coastlines and the ocean floor rose, the wave slowed and grew, stacking up on itself like traffic in a jam. By the time it struck land, walls of water reached heights of 100 feet in some locations, arriving with the force of a liquid mountain moving at highway speeds. Tsunami warning systems now monitor the Pacific Ocean constantly. But in 2004, no such system existed in the Indian Ocean. People in Banda Aceh, Indonesia, had only minutes of warnings. Some noticed the ocean withdrawing far beyond the normal low tide line, exposing fish and coral, a deadly invitation to the curious. In Thailand, tourists walked out onto the exposed beach to collect stranded sea creatures. Then the ocean returned with apocalyptic fury. Now we know, when the sea retreats unexpectedly, run for high ground immediately. The ocean is inhaling before it screams. Earthquakes can trigger other earthquakes thousands of miles away. The 1992 Landers earthquake in California, magnitude 7.3, triggered small quakes in Nevada, Wyoming, and even Yellowstone National Park, put to 800 miles distant. Scientists call this phenomenon dynamic triggering, caused by seismic waves from one earthquake temporarily stressing faults elsewhere. It's as if the entire planet is connected by invisible springs, so that pulling on one creates tension everywhere else. The Earth is not a collection of separate parts, but a single, interconnected system that remembers every tremor. Yellowstone National Park sits atop a supervolcano, and earthquakes there are monitored with particular intensity. The Yellowstone caldera experiences roughly 1,500 to 2,000 small earthquakes each year, most far too subtle for tourists to notice. These tremors result from magma movement and hydrothermal activity beneath the park. While sensational media sometimes predicts imminent eruption, scientists estimate the annual probability of a major Yellowstone eruption at roughly 1 in 730,000. You're far more likely to be struck by lightning multiple times than to witness Yellowstone's awakening. The new Madrid seismic zone in the central United States produced 3 of the most powerful earthquakes in American history, all within 3 months in 1811 to 1812. These quakes, estimated at magnitude 7.0 or greater, rang church bells in Boston, 1,000 miles away. The Mississippi River temporarily ran backward as the land surface warped. Eyewitnesses reported the ground rolling in visible waves like the ocean, trees snapping like gunshots, and sand blows shooting geysers of liquefied earth into the air. The shaking was felt over 1 million square miles, roughly 1/3 of the entire United States. What makes New Madrid remarkable is its location. Unlike California's San Andreas or Japan's Pacific coast, the New Madrid zone sits in the middle of a continental plate, far from any plate boundaries. Scientists still debate exactly why earthquakes happen here, in the stable interior of the North American plate. The leading theory suggests ancient weaknesses in the crust, scars from continental rifting that almost tore North America apart 500 million years ago. These healed wounds occasionally remember their trauma and open slightly, reminding us that no place on Earth is completely immune to seismic fury. Liquefaction turns solid ground into quicksand within seconds. During intense shaking, water-saturated soil loses its strength and behaves like a liquid. Buildings constructed on liquefied ground sink, tilt, or collapse as their foundations lose purchase. Entire neighborhoods have been observed sliding downhill during earthquakes, riding waves of liquefied soil like surfers on a deadly ocean of earth. The 1964 Alaska earthquake produced spectacular examples. Houses rotated 180 degrees, roads buckled into accordion folds, and cars sank into suburban streets as if into tar pits. That Alaska earthquake, magnitude 9.2, remains the most powerful ever recorded in North America. The shaking lasted approximately 4 minutes in eternity when the ground beneath you transforms into a violent sea. The quake raised some sections of coastline by 38 feet and dropped others by 8 feet, permanently redrawing Alaska's geography. It generated a tsunami that killed people as far away as Crescent City, California, and even caused water to slosh around in swimming pools in Texas, 2,500 miles from the epicenter. Earthquake early warning systems can provide seconds to minutes of warning before shaking arrives. Mexico City's system has saved countless lives by detecting earthquakes along the coast and sending alerts to the capital city 200 miles inland. Even 30 seconds of warning allows people to drop, cover, and hold on to stop surgeries, halt trains, and open fire station doors so they won't jam shut. Japan's system automatically slows bullet trains and shuts down industrial facilities when earthquakes are detected. These precious seconds come from the fact that electronic signals travel at the speed of light, far faster than even the quickest seismic waves traveling through rock. The word earthquake appeared in English around the 14th century, but humans have been experiencing and documenting earthquakes for at least 4,000 years. Ancient Chinese records describe earthquakes as early as 1831 BCE. Greek philosophers debated their causes, with Aristotle proposing they resulted from winds trapped in underground caverns seeking escape. Remarkably insightful for someone working without modern instruments. The ancient Romans had no word for earthquake magnitude, but developed a scale based on observable damage, foreshadowing modern intensity scales by nearly 2,000 years. The first seismometer was invented in China in 132 CE by Zhang Heng, a mathematician, astronomer, and poet. His device consisted of a bronze vessel with 8 dragon heads arranged around its circumference, each holding a bronze ball in its mouth. Inside, a pendulum would swing during an earthquake and trigger one of the dragons, to release its ball into the mouth of a bronze toad below, indicating the direction of the quake. According to historical records, the device successfully detected an earthquake 300 miles away that was too subtle for people to feel. Modern replicas have proven the design's effectiveness, a testament to ancient engineering genius. Modern seismometers can detect ground movements smaller than the diameter of an atom. These exquisitely sensitive instruments record vibrations caused by earthquakes on the opposite side of the planet. Ocean waves breaking on distant shores, traffic on nearby highways, and even the footsteps of cattle in adjacent fields. They must be installed in vaults deep underground or on bedrock to isolate them from human noise. The data they gather creates a three-dimensional X-ray of Earth's interior, revealing the structure of our planet layer by layer, like geological archaeology. Earth's mantle, convex like water boiling in a pot. Except this water is rock, and the boiling takes millions of years. Hot rock rises from near the core, cools as it approaches the surface, then sinks back down in vast circular currents. This convection drives plate tectonics, pulling plates apart at mid-ocean ridges and pushing them together at subduction zones. The entire cycle might take 200 million years to complete one lap of a slow-motion whirlpool that operates on timescales incomprehensible to human minds. Subduction zones create the most powerful earthquakes, where one tectonic plate descends beneath another. Enormous slabs of cold, dense rock bend and break under unimaginable stress. The Chilean earthquake of 1960, the Alaskan earthquake of 1964, the Sumatra earthquake of 2004, the Tohoku earthquake of 2011 all occurred at subduction zones, all exceeded magnitude 9.0. These regions store strain for centuries before releasing it in minutes of catastrophic violence, the price Earth pays for constantly recycling its surface. The Cascadia subduction zone off the Pacific Northwest coast of the United States hasn't produced a major earthquake since January 26, 1700. We know the date precisely because Japanese records document a tsunami that arrived without any felt earthquake. In Japan, the orphan tsunami must have originated across the Pacific in North America. Tree ring studies and Native American oral histories confirm the timing. Geologic evidence suggests these great Cascadia earthquakes occur roughly every 300 to 600 years and can exceed magnitude 9.0. The zone is now 325 years into its current cycle, and stress continues to accumulate silently beneath the forests of Washington and Oregon. When Cascadia ruptures again, shaking may last 4 to 6 minutes along the coast. Coastal areas could experience tsunamis arriving within 15 to 30 minutes. Seattle, Portland, and Vancouver sit on ground that will amplify the shaking, potentially causing widespread damage to older buildings not designed for such massive earthquakes. Yet life continues normally. People buy homes and raise families, blissfully unaware or choosing to accept the risk. This is the strange bargain of living on an active planet. We make peace with dangers we cannot control. Induced seismicity refers to earthquakes caused by human activities. Reservoir-induced seismicity occurs when the weight of water in large dams increases pressure on underground faults. The most dramatic example occurred at the Koyna Dam in India, where a magnitude 6.3 earthquake in 1967 killed nearly 200 people. Mining, geothermal energy extraction, and wastewater injection from oil and gas operations can all trigger earthquakes. Oklahoma, which averaged 1 to 2 earthquakes of magnitude 3.0 or greater per year before 2008, experienced over 900 such quakes in 2015, linked to increased wastewater injection from oil production. Humans have become agents of seismic change, though our earthquakes pale compared to nature's power. The Richter scale, developed in 1935 by Charles Richter, revolutionized earthquake measurement, but is largely obsolete for large earthquakes. The scale saturates around magnitude 7.0, meaning it cannot effectively distinguish between magnitude 8, 9, or larger events. Modern seismologists use the moment magnitude scale, which accounts for the total energy released by measuring the area of fault rupture, the distance the fault moved, and the rigidity of the rocks involved. This scale has no upper limit and can accurately measure even the largest earthquakes Earth can produce. A magnitude 5.0 earthquake releases energy equivalent to approximately 1,000 tons of TNT. A magnitude 6.0 releases about 31,600 tons, roughly the power of the atomic bomb dropped on Hiroshima. A magnitude 7.0 releases 1 million tons of TNT. A magnitude 8.0, 31.6 million tons. The scale is logarithmic, so each whole number increase represents about 31.6 times more energy. A magnitude 9.0 earthquake releases roughly 1 billion tons of TNT equivalents, several thousand times the energy of all nuclear weapons ever detonated by humanity, and nature produces these events through the simple friction of rocks sliding past each other. The Earth's inner core is solid iron and nickel, despite temperatures exceeding 10,000 degrees Fahrenheit. Pressure at Earth's center reaches 3.6 million times atmospheric pressure, so intense that it forces atoms into solid crystalline structure, even at temperatures that would vaporize iron at the surface. This inner core is roughly the size of Earth's moon and spins at a slightly different rate than the rest of the planet. Scientists estimate it rotates about 1 degree per year faster than Earth's surface, making a complete extra rotation roughly every 360 to 400 years. It's a planet within a planet, independent and mysterious. Earthquake prediction remains the holy grail of seismology, and it remains largely unattainable. Scientists can assess long-term probabilities, estimating, for example, that Southern California has a 75% chance of experiencing a magnitude 7.0 or greater earthquake in the next 30 years. But pinpointing when and where the next big quake will strike with useful precision eludes us. The crust is too complex, too many variables interact, and earthquakes are fundamentally chaotic events. Every earthquake changes the stress field for neighboring faults in ways we struggle to calculate. The Earth keeps its schedule secret. Some faults creep continuously rather than breaking in earthquakes. The Hayward Fault in the San Francisco Bay Area creeps at about 0.2 inches per year in some sections, slowly but constantly relieving strain. Curbs in the cities of Hayward and Fremont are offset by several inches where the fault passes through neighborhoods. Homeowners can watch cracks gradually widen in their foundations year by year, a slow-motion earthquake that never stops and never becomes violent. Scientists debate whether encouraging more faults to creep might prevent catastrophic earthquakes, but we lack the technology to fundamentally alter how faults behave. We are observers, not directors, of Earth's geological drama. The 2010 Haiti earthquake killed over 200,000 people despite measuring only magnitude 7.0 A powerful quake, but not among history's largest. The catastrophic death toll resulted from a tragic combination: dense population, poor construction quality, lack of building codes, and an epicenter only 15 miles from Port-au-Prince, the capital city. Buildings collapsed into powder, trapping hundreds of thousands in rubble. The disaster illustrated a harsh truth: earthquake danger depends less on magnitude than on human vulnerability. A magnitude 7.0 in a well-prepared society might kill dozens. The same quake in an unprepared nation can kill hundreds of thousands. Moonquakes occur on our lunar neighbor, though they're generally much weaker than earthquakes. The Apollo missions installed seismometers that detected thousands of shallow moonquakes, deep moonquakes, thermal moonquakes caused by the sun's heat and meteorite impacts. Deep moonquakes occur about 700 kilometers beneath the lunar surface and seem to follow a monthly cycle, suggesting they're triggered by Earth's gravitational pull, the same force that creates our ocean tides. Even in the silent vacuum of space, our moon trembles, and Earth is the cause. Buildings can be designed to dance with earthquakes rather than resist them rigidly. Base isolation systems place buildings on bearings or shock absorbers, allowing the ground to shake while the structure above remains relatively still. Taipei 101 in Taiwan, one of the world's tallest buildings, contains a 730-ton tuned mass damper, a gigantic pendulum that swings opposite to the building's movement, counterbalancing earthquake and wind forces. During the 2011 Tohoku earthquake, buildings in Tokyo swayed dramatically but remained standing, their flexible designs absorbing energy that would have shattered rigid structures. Traditional Japanese architecture achieved earthquake resistance through elegant simplicity. Temples and shrines were built with wooden frames that fit together without nails, allowing the structure to flex and absorb shaking. Heavy roofs were intentionally designed to shift during earthquakes, dissipating energy. Some 5-story pagodas built over 1,000 years ago still stand, having survived countless earthquakes that destroyed modern buildings nearby. These ancient builders understood principles that modern engineers are only now beginning to fully appreciate. The United States Geological Survey estimates that several million earthquakes occur each year worldwide. Most are too small to be felt, registering below magnitude 2.0, fewer than 20 major earthquakes. Magnitude 7.0 to 7.9 occur annually on average, and one great earthquake magnitude 8.0 or higher strikes roughly every year or two. But these statistics offer no schedule, no promise that next year will match the average. Some years pass without any great earthquakes. Other years deliver multiple catastrophes. Randomness governs when the ground will break, and averages provide cold comfort to those in the wrong place when the planet decides to shift. Turkey lies on one of the world's most dangerous fault systems, where the Anatolian plate is being squeezed between the Eurasian and Arabian plates. The North Anatolian Fault has produced a westward migrating sequence of magnitude 7.0 plus earthquakes throughout the 20th century, like dominoes falling in geological slow motion. Each earthquake increased stress on the fault section to the west, making the next quake more likely. Istanbul, a megacity of 15 million people, sits at the western end of this sequence, and scientists estimate a 60% chance of a magnitude 7.0 plus earthquake affecting the city in the next 30 years, a ticking clock that cannot be stopped, only prepared for. Seiches are standing waves in enclosed or semi-enclosed bodies of water triggered by earthquakes, landslides, or even atmospheric pressure changes. The 1964 Alaska earthquake caused seiches in swimming pools in Texas and water wells in South Africa. Lakes can develop rhythmic sloshing that continues for hours after the earthquake ends, like water in a bathtub after someone gets out. The phenomenon is predictable. Each body of water has a natural resonance frequency, but seeing it happen during an earthquake reminds us that water remembers the shaking long after solid ground has stilled. Earthquake lights are mysterious, luminous phenomena sometimes reported before or during earthquakes. Witnesses describe blue or white flashes in the sky, orbs of light, or glowing aurora-like displays. Scientists remain skeptical but intrigued. One hypothesis suggests that stress on quartz-bearing rocks generates electrical charges that escape through cracks and ionize the air, creating visible light. Another theory proposes that radon gas released along fault lines might cause ionization. The evidence is mostly anecdotal and photographic, difficult to verify or study systematically. Like many earthquake mysteries, the lights hover between myth and science, unexplained but persistently reported. The 2011 Tohoku earthquake shifted Japan by 8 feet toward North America. GPS measurements showed the entire island of Honshu moved eastward, and the seabed off the coast jumped as much as 164 feet horizontally. The quake was so powerful that it changed Earth's rotation, shortening the day by 1.8 microseconds and shifting the axis by about 4 inches. For perspective, large earthquakes routinely make days microseconds, shorter, imperceptible to us, but measurable with atomic clocks. Proof that earthquakes affect not just buildings and lives, but the very rotation of our planet through space. Tectonic plates move at different speeds. The fastest, the Pacific Plate, races along at about 3.5 inches per year. The slowest, like the Eurasian Plate, crawl at less than an inch annually. These speeds seem glacial to human perception, but over geological time, they're breathtaking. At current rates, the Atlantic Ocean widens by about 2 inches per year, the same rate fingernails grow. In 200 million years, the Atlantic will be thousands of miles wider. In 250 million years, Earth's continents may have assembled into a new supercontinent, closing the Atlantic entirely and opening new oceans elsewhere. A cycle that has repeated at least 3 times in Earth's history and will continue long after humanity is forgotten. Earthquakes can create natural dams by triggering landslides that block rivers. These earthquake-dammed lakes, called quake lakes, pose secondary hazards because the dam consists of loose rock and soil rather than engineered concrete. When the lake fills beyond the dam's capacity, it can fail catastrophically, sending a deadly flood downstream. The 2008 Sichuan earthquake in China created over 30 quake lakes, requiring emergency efforts to drain the water safely before the dams collapsed naturally. Earthquakes ripple through time, creating dangers that persist long after the shaking stops. That Sichuan earthquake killed nearly 90,000 people and left 5 million homeless. The quake struck in the afternoon when schools were in session, and thousands of children died when poorly constructed school buildings collapsed. The tragedy prompted a national outcry about corruption and corner-cutting in construction, leading to massive changes in China's building codes. Sometimes the lessons earthquakes teach come written in unbearable loss, impossible to ignore, forcing societies to either adapt or face the same catastrophe repeated. Chile experiences major earthquakes with tragic regularity. Yet, it has developed one of the most earthquake-resilient societies on Earth. Building codes are strictly enforced. Emergency response systems are well rehearsed, and the population is educated about earthquake safety from childhood. When the magnitude 8.8 Mal earthquake struck Chile in 2010, fewer than 600 people died despite widespread damage, a testament to preparation. Compare this to the Haiti earthquake the same year, which was smaller but killed over 200,000 people. Earthquakes are democratic in their destruction, but human choices determine how many will die. The Seattle Fault, which runs directly beneath downtown Seattle, last ruptured about 1,100 years ago. The earthquake raised the shoreline several feet in seconds, created landslides that generated tsunamis in Puget Sound, and toppled trees that we can still see preserved underwater today. Native American oral histories speak of a time when the land became like a canoe in stormy waters. Geological evidence suggests this quake reached magnitude 7.0 or greater. Seattle's modern skyline sits atop this sleeping fault, built in ignorance that later transformed into knowledge, but the buildings remain, and the fault remains, and someday they will meet again. The earth is still ringing from earthquakes that happened days ago. After every major earthquake, our planet vibrates like a struck bell, oscillating in modes called free oscillations. These vibrations are too slow and subtle for humans to feel. The longest period oscillations have cycles of 54 minutes, meaning the ground slowly rises and falls over nearly an hour, but sensitive instruments detect them for weeks after great earthquakes. The entire planet participates in the aftermath, a collective trembling at frequencies far below human perception, the earth humming to itself in deep bass notes only stones can hear. Megathrust earthquakes occur at subduction zones where oceanic plates dive beneath continental plates. These are the monsters of the earthquake world, the only type capable of reaching magnitude 9.0 or greater. The word megathrust itself conveys the violence. Enormous sections of the seafloor, sometimes hundreds of miles long, suddenly thrust upward by 30, 40, even 50 feet in less than a minute. The 2004 Sumatra earthquake ruptured a fault zone 900 miles long, roughly the distance from New York to Chicago, in about 10 minutes. Imagine a crack racing beneath the ocean at nearly 6 miles per second, unzipping the seafloor faster than sound travels through air. But here's what troubles scientists. Megathrust earthquakes may be able to grow even larger than we've observed. The largest recorded quake, Chile's 9.5 in 1960, may not represent nature's upper limit. Computer models suggest magnitude 9.8 or even 10.0. Earthquakes are theoretically possible if enough fault area ruptures simultaneously. We simply haven't been measuring earthquakes long enough, barely more than a century, with modern instruments to know what the true maximum might be. The Earth may have catastrophes in its repertoire that humanity has never witnessed. Strike-slip faults move horizontally, sliding past each other like hands rubbing together. California's San Andreas is the classic example, the Pacific Plate grinding northward past the North American Plate at roughly 2 inches per year. If you stood on one side of the fault during a major earthquake, you'd watch the other side lurch sideways by 20 feet in seconds. A sudden betrayal of the ground's apparent solidity. Fences, roads, streams, anything crossing the fault gets torn and offset, the landscape shredded like fabric caught in opposing gears. Normal faults occur where the Earth's crust is being pulled apart. One side drops down relative to the other, creating steep scarps and valleys. The Basin and Range province of Nevada and Utah is laced with normal faults, stretching the region like taffy being pulled from both ends. The landscape consists of alternating mountain ranges and valleys, each pair created by faulting mountains rising on one side of the fault, while valleys drop on the other. Over millions of years, this extension has stretched Nevada by about 50 miles east to west. The ground beneath the sagebrush and desert slowly tears itself in two. Reverse faults, also called thrust faults, occur where crust is compressed and one block rides up over another. The Himalayas continue to rise because of thrust faulting the Indian plate ramming into the Eurasian plate and crumpling upward like a slow-motion car crash that's been ongoing for 50 million years. Mount Everest gains about 4 millimeters in height each year, pushed skyward by the inexorable collision. In geological terms, the Himalayas are young, sharp-edged mountains still growing, still rising, still shaped by earthquakes that accommodate India's journey northward. Sheer walls and braced frames give buildings strength against lateral forces. During an earthquake, buildings don't just shake up and down, they sway side to side, and this lateral movement causes the most damage. Shear walls are reinforced concrete or masonry walls that resist this sideways motion. Braced frames use diagonal steel members to prevent rectangular building frames from racking into parallelograms. These elements must be carefully distributed throughout a building. Concentrating them in one area creates stiffness imbalances that can cause twisting and damage. The building must move as a unified whole, not as disconnected pieces fighting each other. Soft story buildings are particularly vulnerable to collapse. A soft story lacks the shear walls or braced frames that exist on other floors, creating a weak point. Classic examples include buildings with ground floor garages or retail spaces that have large openings and fewer walls than the residential floors above. During earthquakes, the soft story deforms excessively, while upper floors remain relatively rigid, concentrating damage at the weak floor and often causing complete collapse of the building above. Thousands of such buildings exist in California and elsewhere, a legacy of older building codes. Retrofitting them is expensive, but far cheaper than the lives lost when they inevitably fail. Unreinforced masonry, buildings, brick and stone structures without steel reinforcement, are death traps in earthquakes. The 1933 Long Beach earthquake in California killed 120 people, many in unreinforced masonry schools that collapsed during the school day. The disaster prompted California's Field Act, requiring seismic design for school buildings. Nevertheless, thousands of unreinforced masonry buildings remain standing in earthquake zones, many now converted to apartments, stores, or restaurants. They survived past earthquakes through luck, not design, and they await the next strong shaking, like condemned prisoners who don't know their sentence has been pronounced. California's building codes have evolved through tragedy. Each major earthquake revealed new vulnerabilities, prompted new requirements. The 1971 San Fernando earthquake collapsed newly built hospitals and freeway overpasses, leading to stricter standards for critical facilities. The 1989 Loma Prieta earthquake damaged the Bay Bridge and collapsed the Cypress Street Viaduct in Oakland, killing 42 people, spurring massive retrofit programs for bridges and highways. The 1994 Northridge earthquake damaged hundreds of steel frame buildings, thought to be earthquake-resistant, leading to new welding and connection requirements. The codes are written in laws, each paragraph a lesson learned in rubble and grief. Japan's building codes are among the world's strictest, yet the country accepts that earthquakes will cause damage. The philosophy is damage, yes. Collapse, no. After the 1995 Kobe earthquake killed over 6,000 people and caused $100 billion in damage, Japan implemented even more stringent codes and began a massive program to identify and retrofit vulnerable buildings. The investment has been enormous, but the 2011 Tohoku earthquake validated the approach despite being one of the most powerful earthquakes ever recorded. The shaking itself killed relatively few people. The tsunami caused the vast majority of deaths. The buildings, largely, did their job. Seismic gaps are sections of active faults that haven't ruptured recently, while adjacent sections have. The hypothesis suggests these gaps are storing strain and therefore have higher probability of future earthquakes. The Nankai Trough off southern Japan shows this pattern. Historical records document regular great earthquakes every 100 to 150 years, with ruptures occurring in segments that sometimes break individually and sometimes together. When segments rupture together, the resulting earthquake can exceed magnitude 8.5. The last major Nankai earthquake occurred in 1946. The clock is ticking, and the gap is growing, and Japan prepares for the inevitable day when the ocean floor lurches upward once again. The probability of a major earthquake in California within our lifetimes approaches certainty. The U.S. Geological Survey estimates 75% probability of a magnitude 7.0 or greater earthquake somewhere in California before 2045. For the San Francisco Bay Area specifically, the probability is 72% for a magnitude 6.7 or greater by 2045. These are not distant, abstract risks. They're near certainties for anyone living in California today. Yet development continues, populations grow, and life proceeds with a collective decision to accept these odds. Perhaps this is wisdom, acknowledging the risk, preparing as best we can, and choosing to live fully despite the ground's inevitable betrayal. Soil type determines how violently a building will shake. Bedrock, solid and stiff, transmits seismic waves with relatively little amplification. Soft soil clay, silt, loose sand, amplify shaking significantly, sometimes by factors of 3 to 5. Building codes now account for this, requiring stronger construction on soft soils. But many older buildings were constructed before engineers understood amplification effects, and they sit on the worst possible ground, waiting for shaking they were never designed to withstand. Resonance can destroy buildings that would otherwise survive. Every building has a natural frequency at which it vibrates most easily, determined by its height, stiffness, and mass. If earthquake waves arrive at or near this natural frequency, the building resonates like a wine glass singing under a moistened finger. The vibrations grow and grow, potentially to the point of failure. Tall buildings have lower natural frequencies than short buildings, which explains why the 1985 Mexico City earthquake heavily damaged 10 to -20-story buildings, while shorter and taller structures fared better. The earthquake's seismic waves matched the natural frequency of mid-rise buildings, setting up deadly resonance. Tsunami means harbor wave in Japanese, a name born from observation in the open ocean. Tsunamis are nearly invisible waves, a foot or two high, with wavelengths of 100 miles or more, traveling at jettercraft speeds. Sailors on ships might not even notice one passing beneath them. But as these waves enter harbors and approach shore, they slow down, stack up, and grow. The energy concentrated in a small area transforms into a wall of water that can reach 100 feet high. Japanese harbors have witnessed this phenomenon repeatedly throughout history, the ocean withdrawing, then returning with apocalyptic force, hence the name. The Indian Ocean Tsunami Warning System was established after the devastating 2004 disaster. Now, a network of seismometers and ocean buoys can detect earthquakes and measure changes in sea level, allowing warnings to be issued within minutes. The Pacific has had such a system since 1949. Established after a tsunami generated by an Alaskan earthquake killed 159 people in Hawaii. The technology works, but it requires international cooperation, maintained infrastructure, and educated populations who understand that when a tsunami warning is issued, you move to high ground immediately without waiting to see the wave. Minutes separate life from death. Rogue waves were considered sailors' myths until satellites and instrument buoys confirmed their existence. These monster waves, sometimes reaching 100 feet or more, appear suddenly in the open ocean and can sink large ships. Some scientists now suspect that earthquakes in underwater canyons might generate rogue waves through complex interactions between seismic displacement and seafloor topography. The connection remains uncertain, another mystery in the catalog of earthquake-related phenomena we barely understand. The ocean holds secrets, and earthquakes may write some of them. The Ring of Fire contains 452 volcanoes, from the southern tip of South America through Central America and Mexico, along the west coast of North America to Alaska, across to Japan, the Philippines, Indonesia, and New Zealand. This horseshoe of volcanic fury directly results from plate tectonics, specifically subduction zones where oceanic plates descend into the mantle, melt, and produce magma that rises to create volcanoes. Earthquakes and volcanoes are siblings, children of the same deep forces, manifestations of a restless planet that has never been and will never be still. Volcanic earthquakes differ from tectonic earthquakes. They're generally smaller and caused by magma movement, gas explosions, or rock fracturing due to volcanic processes rather than plate motions. Volcanoes can produce earthquake swarms, thousands of small quakes over days or weeks as magma rises toward the surface. These swarms serve as warnings, allowing scientists to predict eruptions with reasonable success in some cases. Mount St. Helens produced weeks of earthquakes before its catastrophic 1980 eruption, an escalating drumbeat that announced the coming disaster to anyone listening. Harmonic tremor is a continuous, rhythmic, seismic signal often associated with volcanic activity. Unlike the sharp jolt of a normal earthquake, harmonic tremor sounds almost musical when converted to audio, low hum or rumble that can persist for hours or days. It's thought to result from resonating magma or gas moving through conduits in the volcano, the mountain singing as it prepares to erupt. Seismologists monitoring active volcanoes listen for this eerie music, a song that might precede fire and ash. The Yellowstone hotspot isn't fixed to any tectonic plates, a plume of hot rock rising from deep in Earth's mantle, possibly from the core mantle boundary, 1,800 miles below the surface. As the North American plate moves southwest over this stationary hotspot. The plume burns through the crust like a blowtorch through metal, creating volcanic calderas. The Snake River Plain in Idaho shows the track of this hotspot over the past 16 million years, a line of progressively older volcanic remnants stretching from Yellowstone to the Nevada border. In another million years, the hotspot will be beneath Montana, and Yellowstone will be a quiet, extinct caldera slowly eroding away. Infrastructure interdependencies mean that earthquake damage cascades through systems in unpredictable ways. When power fails, water pumps stop working. When water mains break, firefighting becomes impossible. When roads are blocked by debris, emergency vehicles can't reach hospitals. When hospitals lose power and water, they can't treat the injured. When communication systems fail, coordination collapses. Resilient societies build redundancy into critical systems backup generators, alternative water sources, multiple transportation routes, satellite communications. But perfect resilience is impossible, and every major earthquake reveals unexpected vulnerabilities, cascading failures that planners didn't anticipate because the interconnections were too complex to fully map. The economic cost of earthquakes can exceed the physical damage. The 1995 Kobe earthquake caused an estimated $100 billion in direct damage, but the indirect costs, business interruption, lost productivity, supply chain disruptions potentially doubled that figure. Kobe was a major port, and its closure for months redirected shipping throughout East Asia, affecting global trade. Companies went bankrupt. Workers lost jobs. The ripples spread far beyond the shaking, affecting people who never felt the earthquake but suffered its economic consequences. Disasters respect no boundaries, their effects transmitted through the invisible web of modern commerce. Earthquake-resistant construction costs roughly 5 to 10% more than standard construction in most cases. For a $300,000 house, that's $15,000 to $30,000, substantial for individual homeowners, but trivial compared to rebuilding after destruction. Yet the additional cost often feels abstract and unnecessary, money spent to prevent something that might never happen. Developers resist because it reduces profit margins. Buyers balk because competitors offer cheaper alternatives. Politicians hesitate to mandate requirements that increase housing costs. The math is simple, but human decision-making is complex, shaped more by immediate concerns than future possibilities. Seismic retrofit of existing buildings costs significantly more than building correctly from the start. Retrofitting a wood frame house might cost $3,000 to $7,000 for a simple cripple wall anchor, or $15,000 to $30,000 for comprehensive soft story retrofitting. For large buildings, costs can reach millions of dollars. Many owners can't or won't pay, gambling that the building will survive or that the earthquake won't strike during their ownership. The result: thousands of deadly buildings continue to stand in earthquake zones, financial time bombs, waiting for the right seismic trigger to explode into tragedy. Community preparedness varies wildly, even within the same city. Affluent neighborhoods tend to have higher rates of earthquake insurance, better constructed buildings, and well-stocked emergency supplies. Poor neighborhoods often have older, unreinforced buildings, limited insurance, and residents living paycheck to paycheck who can't afford to stockpile food and water. When disaster strikes, existing inequalities amplify. Those with resources evacuate or quickly rebuild. Those without become trapped in cycles of displacement and poverty, that can last years. Natural disasters are democratic in their physics, but cruelly unequal in their consequences. The 2010 Canterbury earthquake sequence in New Zealand destroyed much of downtown Christchurch through an unusual pattern of repeated shaking. The first major quake, magnitude 7.1 in September 2010, caused widespread damage but killed no one. It struck at 4:35 a.m. when most people were home in suburban, wood-frame houses that performed well, but it also weakened buildings throughout the city. When a magnitude 6.3 aftershock struck in February 2011 during lunchtime, the shallower, closer quake caused catastrophic damage to already weakened structures. The CTV building collapsed, killing 115 people trapped inside. The sequence eventually included over 15,000 earthquakes, a relentless pounding that ultimately forced abandonment of much of the city center. Some buildings can survive one earthquake, but not 10, not 100, not 1,000. Christchurch's red zone areas deemed too damaged or dangerous for rebuilding forced thousands of residents to abandon homes and neighborhoods permanently. The government bought properties and demolished structures, leaving large areas of the city as empty land, reverting to nature. Streets that once held families and businesses now lead to nothing, ghost roads in a ghost suburb. This is earthquake's most complete victory, not just destroying buildings, but erasing communities, wiping away the accumulated lives and memories of generations in a bureaucratic decision that follows seismic catastrophe. Liquefaction can make buildings sink into the ground during earthquakes, even when the structures themselves remain intact. In the 1964 Nagata earthquake in Japan, apartment buildings tilted up to 80 degrees nearly on their sides. While remaining structurally sound, residents could have walked on the walls. The buildings later were jacked back upright, and the ground improved, allowing some to be reoccupied. But imagine the surreal horror, being inside a building that's intact but tilting like a sinking ship. Doors and windows no longer level with the horizon. Gravity pulling at strange angles as your home becomes a funhouse nightmare. Sand boils appear when liquefaction forces water and sand upward through cracks in the ground. They look like small mud volcanoes, fountains of wet sand, shooting several feet into the air during strong shaking, then settling into cone-shaped mounds. After the earthquake, these sand boils mark liquefaction zones, like a map written in mud. Some are small enough to step over. Others deposit tons of sand across roads and yards, burying everything beneath a layer of wet gray grit that came from deep underground, the earth turning inside out in spots, exposing layers that should remain hidden. Earthquake reconnaissance teams deploy within days of major earthquakes to document damage before cleanup begins. These engineers and scientists photograph collapsed buildings, measure ground deformation, collect perishable data that will be lost once reconstruction starts. Their work feeds into building codes and seismic design standards, ensuring that each disaster teaches lessons for the future. It's necessary work, but emotionally devastating, walking through destruction, documenting failure, knowing that each collapsed building represents lives destroyed or ended. They carry the weight of these images forever, human costs translated into technical reports that might save future strangers they'll never meet. Moment magnitude measures earthquake size based on the seismic moment, the product of fault rupture area, average displacement, and rock rigidity. A magnitude 9.0 earthquake requires roughly 30 times more energy than magnitude 8.0. which requires 30 times more than 7.0. The progression is exponential, not linear. The difference between magnitude 9.0 and 9.5 is enormous. Chile's 9.5 in 1960 released approximately 2.8 times more energy than the 9.0 Tohoku earthquake in 2011. Nature's most powerful earthquakes dwarf even the most destructive nuclear weapons, tapping into potential energy stored in rock over centuries, releasing it in seconds of unimaginable violence. The energy released by a magnitude 9.0 earthquake equals roughly 32 billion tons of TNT, or about 2,000 times the energy of the largest nuclear weapon ever tested. Yet this energy dissipates quickly through distance. Most of the energy radiates as seismic waves that travel through the planet harmlessly, shaking distant ground imperceptibly. Only a fraction of the total energy causes damage at the surface. If we could somehow capture and use earthquake energy, a single magnitude 9.0 earthquake could power all human civilization for several days. But the energy releases too quickly, too violently, in the wrong place, utterly beyond our control. We are spectators to power we can measure but never harness. Seismometers detect ground motion by suspending a mass on a spring inside a frame attached to the ground. When the ground shakes, the frame moves, but the mass due to inertia tends to stay still relative to space. The difference in motion between frame and mass is recorded as seismic activity. Modern instruments use electronic sensors rather than mechanical pens, detecting movements smaller than an atom's width. Arrays of these instruments around the world continuously monitor Earth's trembling, creating a global nervous system that feels every significant earthquake within minutes of occurrence. The planet is watched, measured, mapped in real time by sensors that never sleep and never stop listening. The shadow zone for S-waves proved that Earth's outer core is liquid. S-waves, which are shear waves, cannot propagate through fluids. They require solid material to transfer their side-to-side motion. When large earthquakes occur, S-waves propagate around the Earth, but create a shadow on the opposite side where no S-waves appear, blocked by the liquid outer core. This observation, made in the early 20th century, provided the first definitive proof that Earth's interior contains molten material. We understood the deep structure of our planet by listening to earthquakes, using seismic waves as X-rays to peer through thousands of miles of opaque rock. P-waves can travel through any material, solid, liquid, or gas because they're compression waves, like sound. They compress and expand material in the direction of travel, squeezing and releasing as they pass. These are the fastest seismic waves, traveling at roughly 15,000 miles per hour through Earth's mantle. They refract as they pass through layers of different density, bending like light passing through water. By studying how P-waves curve through Earth's interior, seismologists have mapped the planet's internal structure with remarkable precision, identifying the boundaries between crust, mantle, outer core, and inner core, complete planetary anatomy derived from vibrations. Surface waves travel along Earth's surface rather than through the interior, moving more slowly than P-waves and S-waves, but often causing more damage. Love waves move the ground side to side, horizontally, like a snake slithering. Rayleigh waves create a rolling motion, moving the ground up and down and forward and backward, simultaneously, the motion that makes people seasick during earthquakes. These surface waves are what people feel most strongly during moderate to large earthquakes, the rolling and swaying that makes buildings dance and the ground seem liquid. The amplitude of seismic waves decreases with distance from the source, but not uniformly. Seismic waves can be focused or defocused by Earth's interior structure, like lenses bending light. Some areas might experience stronger shaking than expected based on distance alone, while others experience weaker shaking. The 1994 Northridge earthquake caused severe damage in Santa Monica, 15 miles from the epicenter, partly because seismic waves were focused by the basin structure beneath the city. Understanding these effects requires detailed knowledge of local geology, information that doesn't exist for many earthquake-prone regions worldwide. Fault creep releases energy gradually, preventing earthquakes or, so we hope. The Hayward Fault in California's East Bay creeps at about 0.2 inches per year in some sections, with curbs, sidewalks, and buildings slowly being torn apart by the constant motion. Scientists debate whether creeping sections of faults are less dangerous than locked sections, or whether they're simply releasing shallow strain while deeper portions remain locked and dangerous. The ground offers no clear answers, maintaining ambiguity that makes risk assessment maddeningly difficult. Fault segments can rupture together in devastating cascades. The 2016 Kikura earthquake in New Zealand ruptured at least 21 different faults in a complex sequence over roughly 2 minutes, producing a magnitude 7.8 earthquake that lifted the seabed by several meters and shifted coastlines northward by up to 18 feet. Fences, roads, and railways crossing the faults were offset by yards, the landscape physically rearranged. The complexity of the rupture surprised seismologists. This wasn't one fault breaking, but an entire fault network, failing nearly simultaneously, like dominoes falling in multiple directions at once. We thought we understood fault behavior. Then nature demonstrated we'd barely begun to grasp the possibilities. Induced seismicity from wastewater injection associated with oil and gas production has made Oklahoma more seismically active than California in some recent years. The mechanism is well understood. Injecting millions of gallons of wastewater deep underground increases pore pressure on existing faults, reducing friction and allowing them to slip. The earthquakes are relatively small. The largest induced earthquake in Oklahoma reached magnitude 5.8 in 2016, but frequent enough to damage buildings and alarm residents who never expected to live in an earthquake zone. Humans have inadvertently learned to trigger earthquakes, a dangerous capability we're still learning to control. Geothermal energy projects have also triggered earthquakes. In Basel, Switzerland, a geothermal project in 2006 injected water into hot rock 16,000 feet underground to create steam for power generation. The injection triggered thousands of small earthquakes, including several that exceeded magnitude 3.0, causing minor damage and significant public alarm. The project was eventually abandoned. The incident highlighted a difficult truth. Many clean energy technologies interact with Earth's crust in ways that carry seismic risk. We cannot escape the ground's response to our intrusions, even when those intrusions serve beneficial purposes. The nuclear disaster at Fukushima Daiichi resulted not from earthquake shaking, but from the tsunami that followed. The reactors successfully shut down when the magnitude 9.1 Tohoku earthquake struck, and the buildings withstood the intense shaking. But the 45-foot tsunami that arrived 40 minutes later overwhelmed the plant's seawalls, flooding basement areas containing emergency generators. With power lost and cooling systems failed, 3 reactors experienced meltdowns over the following days. The disaster released significant radioactivity, forced evacuation of over 150,000 people, and cost hundreds of billions of dollars. It demonstrated that earthquake hazards extend beyond shaking. The secondary effects can be catastrophic, even when primary effects are successfully managed. Seawalls in Japan were built after the 1960 tsunami, designed to protect against waves up to 10 or perhaps 15 feet high. The 2011 tsunami reached heights of 130 feet in some locations, overwhelming defenses that seemed adequate until nature demonstrated otherwise. Concrete walls 30 feet high were topped by waves that kept coming, kept rising, pushing inland for miles. Entire towns vanished. The walls remained standing in places, monuments to insufficient imagination, to the human tendency to prepare for the last disaster rather than the next one, which might be worse than anything we've seen before. The debris field from the 2011 tsunami crossed the Pacific Ocean, washing up on North American shores for years afterward. Everything imaginable floated in that terrible slurry: boats, cars, houses, furniture, personal belongings, bodies. A soccer ball lost by a Japanese boy was found in Alaska, returned to him as a small gesture of connection across the disaster's gulf. The ocean remembers and transports, carrying wreckage across 5,000 miles, distributing tragedy across an entire ocean basin, as if to remind the world that these events are planetary in scale. Climate and earthquakes might interact in ways we're only beginning to understand. Some studies suggest that melting glaciers can trigger earthquakes by removing weight from the crust, causing isostatic rebound, the land rising as ice retreats. Alaska has experienced increased seismic activity as glaciers melt, and Iceland shows a similar pattern. The connection remains uncertain and debated, but if true, it suggests that climate change might alter seismic hazards in unexpected ways. Earth's systems are interconnected at every level, and pulling one thread can set the whole fabric trembling. Sea level rise exacerbates tsunami risk by allowing waves to penetrate farther inland. Coastal areas already vulnerable to tsunamis will become more so as sea levels climb. The combination of subsidence from earthquakes and global sea level rise could permanently flood some coastal regions after major earthquakes, making them uninhabitable. We're entering an era where earthquake risk, climate risk, and sea level risk compound each other, creating vulnerability profiles that would have seemed fantastical a generation ago. The Anthropocene, the proposed geological epoch defined by human influence on Earth, includes our seismic footprint. Future geologists might identify our time by the layer of concrete rubble, the chemical signatures of industrial pollution, and the altered seismic patterns caused by reservoir filling and wastewater injection. We've become a geological force, reshaping Earth at scales usually reserved for plate tectonics and climate shifts. This power comes without wisdom, and earthquakes remind us that the ground still makes its own decisions, indifferent to our presence or preferences. Early earthquake prediction efforts in China during the 1970s had mixed success. The successful evacuation of Hiking in 1975, based on foreshocks and animal behavior, saved thousands of lives, validating the approach. But the 1976 Tangshan earthquake struck without obvious warning at 3:42 a.m., killing an estimated 242,000 people, possibly more, as exact figures remain uncertain. The disaster demonstrated that prediction based on precursory phenomena is unreliable at best. We can identify heightened risk, but cannot specify when and where with enough precision to justify evacuations or emergency measures. False alarms carry their own costs. If authorities evacuate a city based on earthquake predictions and no earthquake occurs, credibility erodes. If they issue too many warnings that prove false, people stop responding. The boy who cried wolf, except with entire populations and the stakes measured in lives. This creates a paralyzing dilemma. Issue warnings and risk false alarms that breed complacency, or stay silent and risk catastrophe that might have been partially mitigated. There's no clean answer, only difficult choices with uncertain outcomes. Some scientists propose drilling into faults to relieve pressure before major earthquakes occur, or to lubricate faults with injected fluids to promote gradual creep rather than sudden rupture. These ideas remain speculative and controversial. We lack the technology to drill deep enough, and the risk of accidentally triggering a major earthquake while trying to prevent one seems unacceptably high. We are not yet gods of the underworld, not masters of the tectonic realm, and perhaps we should be grateful for our limitations. Some powers might be better left unwielded. The psychological comfort of earthquake mythology persists across cultures. Many societies have myths of giant creatures, underground dragons, turtles, catfish, serpents whose movements cause earthquakes. These stories served psychological and social functions, providing explanations and rituals that gave people a sense of control or at least understanding. Modern science has replaced these creatures with plate tectonics and elastic rebound theory. But the emotional need remains the same. We want earthquakes to have meaning, to fit into narratives we can comprehend. The ground shakes randomly, but humans require stories. The Lisbon earthquake of 1755 profoundly impacted European philosophy. The earthquake struck on All Saints' Day, when churches were full. Thousands died when churches collapsed, raising agonizing theological questions. Why would God destroy the faithful at worship? The disaster influenced Voltaire's Candide, which satirized the philosophical optimism that claimed we live in the best of all possible worlds. How could a world where earthquakes kill indiscriminately be the best possible? The question still echoes. Natural disasters pose profound challenges to any worldview that requires the universe to be fundamentally just or purposeful. Earthquakes reveal uncomfortable truths about existence's randomness. Good people die in earthquakes. Bad people survive. Careful preparation helps, but doesn't guarantee safety. Careless disregard is often rewarded with undeserved luck. The ground's movements follow physics, not morality. This randomness disturbs us deeply. We want to believe that virtue is rewarded and vice punished, that preparation prevents catastrophe, that the universe operates according to principles we can influence. Earthquakes remind us that we are small and the cosmos is indifferent. Yet humans persist in earthquake zones, generation after generation. Istanbul, Tokyo, Los Angeles, Santiago. Millions live in cities virtually certain to experience major earthquakes eventually. We stay for reasons both practical and profound: economic opportunities, family connections, cultural heritage, sheer stubbornness. We accept risk as the price of place, choosing to love locations despite their dangers. This might be foolishness or courage, perhaps both, but it's deeply human. This refusal to be driven away by fear, this insistence on calling home places that might destroy us. Children born in earthquake zones grow up with different relationships to stability than those raised on quiet continental interiors. They learn early that the ground can betray you, that safety is provisional, that in seconds everything can change. This awareness can create anxiety or resilience, often both. Some leave for calmer ground when they're old enough. Others stay, the seismic uncertainty woven into their identity, an accepted aspect of life's texture. We are shaped by our environments in ways both obvious and subtle, and living where the earth moves changes how you move through life. The Nazca Plate dives beneath South America at 2.4 inches per year, driving the Andes Mountains higher and loading stress on the Peru-Chile Trench, source of multiple magnitude 9.0 plus earthquakes throughout recorded history. The plate will continue subducting for tens of millions of years until eventually the Pacific Ocean closes an inconceivably distant future where South America and Asia might collide, creating new mountains that dwarf the Andes and Himalayas. These timescales mock human concerns. Yet, in the present moment, the subduction continues, and the earthquakes come, and people build lives in the shadow of mountains that rise millimeter by millimeter from ancient violence. The Juan de Fuca Plate off the Pacific Northwest is young, warm, and relatively small only, about 250 miles wide. Yet this modest plate poses outsized hazards as it slides beneath North America at roughly 1.6 inches per year. The Cascadia subduction zone, where the plates meet, has produced at least 41 major earthquakes in the past 10,000 years. Based on turbidite deposits, underwater landslide sediments triggered by quakes. These events occur roughly every 200 to 800 years on average, but the intervals vary wildly. The last was in 1700. The next could strike tomorrow or 500 years from now. The plate offers no schedule, only certainty that it will happen eventually. Paleoseismic trenching across the San Andreas Fault near Los Angeles reveals a complex history. The fault doesn't rupture regularly or predictably. Some earthquakes happen in clusters separated by centuries. Others occur as isolated events. The southern San Andreas hasn't produced a major earthquake since 1680, over 340 years of accumulating strain. Physics suggests the fault is overdue, but faults don't follow human concepts of scheduling. The strain continues building, day by day, inch by inch, until the friction can no longer hold. Then it will snap, and Los Angeles will discover what its buildings can withstand. The Wasatch Fault in Utah threatens Salt Lake City with similar quiet menace. The fault last ruptured in segments between 400 and 2,500 years ago, and geological studies suggest it produces magnitude 7.0 plus earthquakes every 1,000 to 1,500 years on average. The city, home to over 1 million people, sits directly on the fault. Many buildings predate modern seismic codes. When the fault next ruptures, and it will, the results could be catastrophic for the unprepared and survivable for those who've taken the threat seriously. The choice belongs to residents and policymakers who must decide whether future possibilities justify present costs. Every earthquake permanently changes the landscape. Rivers are redirected, coastlines shift, mountains rise or sink, lakes appear where none existed, falls drain away. The surface we inhabit is temporary, constantly being rewritten by tectonic forces operating on timescales that exceed human civilization's entire span. The very concept of permanent geography is illusion. The map of Earth 10 million years from now will be unrecognizable, redrawn by endless earthquakes and the plate motions they accommodate. We are passengers on a ship that constantly rebuilds itself, never arriving at any final form. Earthquake science has advanced enormously in the past century, yet fundamental mysteries remain. We can't predict earthquakes precisely. We don't fully understand what determines maximum magnitude on any given fault. We can't explain why some faults creep and others lock. We struggle to forecast aftershock sequences or understand triggered seismicity at great distances. Each major earthquake reveals something unexpected, some behavior that doesn't fit existing models. Nature is inexhaustibly complex, and the more we learn, the more we realize how much remains unknown. This is both humbling and thrilling. The ground beneath us still holds secrets, still surprises us, still teaches us that we are students who will never graduate. The study of earthquakes connects to everything: geology, physics, engineering, psychology, economics, politics, history, philosophy. Earthquakes aren't isolated phenomena, but intersections where Earth's physical processes meet human civilization. Understanding them requires crossing disciplinary boundaries, integrating knowledge from fields that rarely communicate. The seismologist must understand rock mechanics. The engineer must understand human behavior. The policymaker must understand probability. The citizen must understand risk. No single perspective captures the full picture, and wisdom lies in synthesis, in seeing how physical facts translate through layers of interpretation into lived experience. As you drift toward sleep tonight, the ground beneath you moves imperceptibly, continuing its patient crawl across the planet. Stress accumulates in locked faults, energy stored like compressed springs waiting for release. This is neither threat nor comfort, simply fact, the physical reality of living on an active planet. Earthquakes have shaped the landscape you inhabit, thrust up the mountains you admire, carved the valleys where rivers flow. They've destroyed cities and killed millions across history, yet they've also driven evolution, created mineral deposits, recycled continents, and made Earth the dynamic, living world that gave rise to you. Fear is natural, but need not be consuming. The ground will shake again in California, in Japan, in Turkey, in places we haven't identified as at risk. Some will die, and that's tragedy. But most will survive, and communities will rebuild, and life will continue. Humans have endured earthquakes since long before we had words for them, and will endure them until our species passes from this world. We are resilient, adaptable, capable of learning and preparing. The earth moves beneath us, but we've learned to dance with its motion, to build structures that sway rather than shatter, to accept uncertainty while still choosing hope. The earth is old 4.5 billion years, and has been shaking itself for most of that time. Long before the first humans walked upright, earthquakes rattled the land. Long after our last descendant is gone, the plates will continue their slow drift, and faults will continue to rupture, and mountains will continue to rise from the patient violence of stone grinding against stone. We are temporary witnesses to eternal processes, privileged to live in this precise moment when consciousness can observe and understand the mechanisms that shape worlds. That awareness is a gift, even when the knowledge reveals dangers we cannot prevent. Close your eyes now. Feel the stability of your bed, the solid floor beneath, the reliable ground under the foundation. All of it rests on rock that floats on rock, that flows on rock, that melts. All of it moves invisibly, constantly, participating in a dance that predates mountains and will outlast oceans. You are made of earth calcium from shells compressed into limestone, iron from long-dead stars, water that has cycled through rain and rivers, and the bodies of creatures extinct for millions of years. The atoms composing your body have witnessed countless earthquakes from various perspectives, sometimes as stone, sometimes as sea, sometimes as life. You are, in a sense, the earth examining itself, asking questions about the ground you're made from. The mystery and the wonder remain. Why does Earth alone among the planets have plate tectonics? Why do faults sometimes creep and sometimes snap? Why does the inner core rotate at a different speed than the surface? We have theories and models, but certainty eludes us. The Earth keeps secrets, reveals them slowly, playfully, through disasters and through patient study. Every earthquake is a message from the deep interior, a communique from realms we cannot visit, written in the language of waves that travel through rock. We're learning to read this language, but we're still beginners, still surprised by what we find. As sleep comes, let yourself imagine the grand sweep of geological time. Continents that were joined before mammals evolved have drifted thousands of miles apart. Mountains that once rivaled the Himalayas have eroded to stumps. Oceans have opened and closed. Species arose, flourished, and vanished. Through all of it, earthquakes marked the rhythm, the percussion in Earth's long symphony. You are a single note in that endless music, brief and beautiful and irreplaceable. The ground that bore you will hold you tenderly, will shake sometimes and be still mostly, will support your life until that life concludes and returns to the patient stone. Good night, dear friend. May your rest be deep and peaceful, undisturbed by tremors. May you wake to a morning where the ground is stable and the day is full of possibility. And may you carry forward a sense of wonder at this improbable planet we call home, dangerous and beautiful, violent and nurturing, ancient and ever new. The Earth spins through darkness, bearing all of us on its surface, a ship sailing an endless night sea toward no destination except tomorrow and tomorrow and tomorrow. The earthquakes will come when they come. For now, there is only stillness and breath, and the gentle descent into dreams, where the ground never shakes, and mountains stand forever, and all the lost are found again. Sleep well.